Good morning, Nick.
Good morning, Leon.
So what are you doing?
I'm just putting our EP, estimated position, on our chart.
Oh, that's good. Dead reckoning.
Yes, that's right.
Or
yes.
estimated position.
Estimated, yes, that's right, yeah. And so our base point we did yesterday, we did 2 back bearings against Cape Finisterre and one of the lighthouses on the coast, and that gave us our start position. And then we've used our track in the log. So we've been recording pretty much as we go, our distance and course. And then what we're going to do is translate that information from our base position to the estimated position this morning. And so if we look at that, what we have is an EP here, and that's based on a track where we change course a number of times in the night based on the shifting wind. So this is our EP position for our forward calculations, which we're going to start now.
Okay, well done. So I'm going down to check the chronometer at the same time, in the meantime.
Yeah, okay.
It's all on UTC, of course, and then I compare my little clock here, and I can see 40. So it is, my watch which I'm going to use is 3 seconds fast. So I have to deduct 3 seconds, and that's not a problem because that is not very accurate, the little one, but that is accurate. So I have to deduct 3 seconds from when I've done the sunshot. So that's good. So I'll put that back. And that I don't have to do every day because it won't drop so much seconds, but it's always good to do. So that's my chronometer. And I'll take out my sextant for my morning shot. It's a bit cloudy, but I hope it's gonna shine through. We have an occluded front here today. Nick, would you mind taking the time and note down the time, because it's good to be 2. So absolutely, what you could do is then that you note down first the seconds, then the minutes, and then the hours in UTC when I shout now.
So here I sit on the coach roof, which is a very nice place to sit, very comfy. I know how high I am above the sea level because I've measured that. That's 2.8 meters actually, or 2.5. I made a note out of it. So first thing you have to do is to check the index error. So you put your sextant on 0 degrees and 0 minutes, and that's just to check if it is measuring correctly. It's called the index error. So I'll lift this up and I do it so it is crisp and sharp, and then I look and turn this so I only have one horizon, and then I can look up and see that it is exactly 0 degrees and 0 minutes. And that doesn't come as a surprise because the Customs and Plat sextant has a little red button here, knob, that I can open that and freely adjust this one, so I take out the index error completely. So that's good. So now it's a bit cloudy, so it's a bit difficult to get a good sun shot. But my way of doing this is that I estimate the altitude of the sun, and I estimated it to be about, I don't know, 40 degrees or something. So now you mustn't forget to put the shades on there. And here on the Customs and Plat sextant I actually have a shade which is chronometric, meaning that it has a Polaroid filter, so you can dim it up and down the sun, so to speak. So I put it around 40 degrees here, and then I go to that place where it is the crispy on the horizon, and then I move my level up, and then I can see I can see the sun. That's really cool. I can actually. So now, in order to see that it is exactly on the horizon, kissing the horizon, I have to move and tilt the sextant like this. But I can also open up my Schiller prism here, and I don't have to do that on the Customs and Plat sextant because then it tells me exactly where it is. So I'm quite ready here, Nick. If you are ready to take the time, I say now, and then you check on the.
Yep, good.
So I would say, where is it? Now. So now let's see what I've measured. So you can see here, these are the degrees and these are the minutes. So it is very important that you round down the degrees always, because it looks as if it's 39 degrees, but it's not quite 39 degrees. It's 38 degrees something. There's something you read off here. So always round down to the nearest degree. So this would be 38 degrees and 41 minutes. Because if you look here, if you you just have to turn this much, and then you are in the next full degree, which would be 39. But we are not quite there. We're here at 41. So this is what we're going to note down as the HS, the measured altitude or angle between the horizon and the sun on the sextant. So now I'm here sitting doing the calculations of what else do you do on the middle of the Atlantic, going MERV 4.5 knots with beautiful weather, no waves, just a little swell, days to go, and just one day into our adventure sailing from Galicia with two great friends, Nick and Tom, to the Azores. So Nick has been kind enough to do an EP here on the chart, so that's good. So I will use that information in a second. And then the whole sight reduction of the sun, I have made a great template here. Well, I think it's great. It's been taking decades to develop it. It has everything on one A4 page, and I hope it will be published by Customs and Plat in due course. Nevertheless, I won't fill this in on the paper right now because it's a bit easier if I fill it in on electronic paper for you, because then you can do a screenshot at the same time. So I'm using my Remarkable, which is now doing the screen capture, so we can then see exactly what we're going to do. So the whole thing goes in 5 steps. So I have step number 1, that is the measurement and the data which was valid at the time of shooting. Then I have to determine as step number 2 the position of the sun in correspondence with myself, in order so I can then find an assumed position for which I can use step number 3. And step number 3 is a sight reduction table where I will find the calculated altitude, HC, and the azimuth. And then I will compare the calculated altitude for that position with my own observation. And these two are then compared in step number 4. And step number 5 is then drawing it into the chart. And the easy part is that all you have to do is that you only look into that red box when you draw into the chart. Disregard from anything else, because it's just this what you draw into the chart. And as soon as something red pops up here, that's a result for the red box that then goes into the chart. So let's begin. So I start at step number 1 here. So it's the date. So that's the 16th of June 23. And now the estimated position, latitude and longitude, that's what Nick did. So Nick, can you give me your estimated position in lat and long?
The EP is 42 degrees 29 minutes north.
42 degrees 29 minutes north.
And 010 38 west.
West. That's where we estimate that we are, due thanks to the dead reckoning, or taking a little bit the current into consideration. It's some ocean current going southbound here. Well, the time of the shooting, that was?
That was at 8:08.
08.
Sorry, 08:53.
53.
And 40 seconds on the watch.
40 seconds on the watch, but
we have to subtract 3 seconds to correct the watch against the chronometer.
Yes, because my little Casio was going 3 seconds fast. Good, so I've corrected that there. The log, that's good to know, because that's when we shot it.
The log is 142.
142, oh, that's quite a good distance that we have made. And despite the very weak winds and very calm weather, it's very benign and very pleasant Atlantic crossing, I must say. Well, half crossing at least. So the course over ground and speed over ground, that's how we're going to move forward. So what do we think that we're going to do from here? Now, what's the direction towards the Azores? 260, is it?
260, yeah.
That's right, 260 degrees. And what speed? Well, it's not very fast. Let's put it 4.5 knots. Maybe we need to motor later on. We're getting into the Azorian high here. Good. So that's that. So now see what altitude we had on the sextant. That was my job. So remember, that was 38 degrees and 41, right? 41 minutes on the sextant, HS. So the index error, well, it's a Customs and Plat, and we can deduct that. So it doesn't have any index error. So that means that the observed altitude is 38:41 minutes. From here, there are 2 ways. Either, I call it here the R way, the traditional, slow, maybe accurate way. But if you do it the simple way and just do an approximate
correction of all these things here in one go, the error for Northern Hemisphere summers sitting on the coach roof with 2.5 meters above water, the maximum error can only be 0.3 minutes, corresponding to 0.3 nautical miles. Of course, if you want to do it precisely, but we can't measure that precisely on the Sextant, and most watches aren't that accurate. Not everyone has a chronometer, so you would have taken your Casio and you would have been 3 seconds off anyway. But let's do both ways and compare them. So the traditional way is 38 degrees and 41 minutes. So we have to take the dip into consideration. The dip is the height of the eye. So I didn't remember it when I was sitting shooting, but I have it here now. So sitting on the coach roof, that is 2.5 meters above sea level. So that's what is valid on my boat. So if you go here and look, 2.5 meters, that is a correction of 2.8 minutes, negative 2.8 minutes. So I'll write that here, 2.8 minutes. So we have to deduct that because the dip is always negative. So now we deduct that and do the calculation. So this means that I have to do it here, 3, 7, 8, and then we have 38 degrees and 38.2 minutes is the apparent altitude. Now we need the sun correction, that is for the semi-diameter and the refraction. So we have to look that it is in summer here, April to September. And remember, the fraction is dependent on the altitude of the sun. So we go down here to about 38 degrees, 38. That's about in between here. So it's plus 14.8 minutes. So it's always plus 14.8 minutes. So we add these together. 8 plus 2 is 0. That makes it nice and simple. So that is, then we add, that is 12, that is 13, 3, 4, 5. So it's 38 degrees 53.0. So that's what is expected from you from the RYA when you do your Yachtmaster Ocean. Now let's do it the simple way, just for the fun of it. So we take the 38 degrees 41 here, and then we see here, how far down do we go? Well, we are about 40 degrees more or less that we shoot the sun, the altitude. So we have to add 12. So all we do is we add 12 here, and you bet it's the same result. So this thing here is really a good thing to use actually when you are seasick or just want to do it a quick approximation. But beware, the RYA is asking you to do it the long way. And if you don't really remember what all these things are and how you look it up, here I have my footnotes. So it then gives you hints where you can find different informations. So first step is done. That's nice. So let's go to the second step. So we determine the position of the sun and the ship, and then we try to find a assumed position as closest to our estimated position as possible, for which we can go into the site reduction table. So remember, the site reduction table is made for the latitude of your position to a closest degree. It is made for the declination of the sun, and it's made for the local hour angle, that is the relative position between you and the sun. That's why we have to determine the local hour angle, which some people think is a bit awkward, but it makes sense if you use it a couple of times. The easy thing is that your assumed positions, the latitude of the assumed position, that just needs to be the full degree. So 42 degrees and 39 minutes. Well, the closest full degree, that is 42 minutes, and I put 00 here. That is a red text here, so that drops down here immediately. So that's my first catch. So my assumed position is on latitude 42. Then I need to see what the declination is of the sun today. So, all right, so I'll look here, 8:53. What's the declination of the sun? And here it gives a hint, interpolate by eye, because the sun is going so slowly in its declination, which is the sun's latitude. So 8:53, and in the book it's given for every hour. So what we have to do here, you take the nautical almanac of this year, and I've already made a little mark here. That's a good hint to do that. So you quickly find the day of today. So that quickly. So here we have the 16th of March, and all you have to bother about
June.
16th of June. Sorry, thank you, Nick. 16th of June, and all you have to bother about is these two figures which belong to the sun. The whole spread is for these 3 days, but it's about the planets, about the moon, twilight, loads of information of today. We only need the sun and the declination of Greenwich hour angle. So if you look at 8 o'clock, it has a declination of north 23 degrees and 20.5 minutes north. And at 9 o'clock, it has a declination of 23 degrees and 20.6. So it's only a 0.1 difference. And the site reduction table anyway only takes declinations by the full minute. So you don't have to bother about the decimals at all, because the site reduction table isn't that precise. Okay, so it's closer to 9 o'clock. Let's round it up to 21 minutes. So 23 degrees and 21 minutes. 23 degrees and 21 minutes north. And we are also on northern latitude. So we are actually both on the same hemisphere. So that was easy. So now we know the declination of the sun. Now, the Greenwich hour angle isn't that easily determined, because while the declination changes very slowly, especially in midsummer, the Greenwich hour angle, which is the longitude of the sun, that is really fast. So we can't just do it by eye. Theoretically we could, because we know that every hour the sun moves on 15 degrees. But we have these wonderful tables that help us to do that. So we look up again. So now we look at the first column. So it's the 16th of June. It is at 8 o'clock. We have one Greenwich hour angle. It's 299.50.3. And then at 9 o'clock, we have 314 degrees and 50.1. So that is a huge difference. So what we have to do is we round down. So we take the one for 8 o'clock, and then we look what do the minutes and seconds give us in addition to that. That's the increment. So we'll start to write down 299.50.3. 299.50.3. And if you ask me, never mind these 0.3. But since we are in the RYL world, well, let's continue like that. And then we have to see in the increments. The increments are, if you go back with the arrow, it's about the minutes and the seconds. So we have to go back here in the back of the book. Here are the increments for 18, 19 minutes, but we are at 53 minutes. So that is in the very back here, 53 minutes. So we are at 53 minutes, and here again, that is 53 minutes. These are the seconds, and we only need to take the sun into consideration. So 53 minutes and 37 seconds. That's when we shot it. So in these 53 minutes and 37 seconds, the sun has continued to move 13 degrees 24.3. And that comes as no surprise, because at 1 hour is 15 degrees, as I said. So 13 degrees 24, right there, 13 degrees 24.3. So when we add these together, we have them at the full hour, and then the increments. So these two become 0.6. This becomes 4. Here you have to be careful. It goes one of these two make a full degree, and the other one is the 10 that we leave. So 70 minutes is 1 degree and 10 minutes. So we have 1 degree here. So 9, and then we have 12, and then we have 13. 9, 10, 11, and then we have 313 degrees. So that's good. So now we know where the sun is. So now comes the challenging bit, to understand what the local hour angle is. The local hour angle is the difference between the longitude of the sun, which is called Greenwich hour angle, and our longitude. And for that sake, I've made a little sketch here. So you look from the Earth from the top. So this is the North Pole. You have the meridian here. So this is England, and I don't know, the Caribbean is about here. So these are western longitudes, or the Greenwich hour angle, which is always western. So which longitude do we have? We have 10 degrees west there. So you can draw a little boat here. That's where we are approximately at 10. So this is our longitude. Well, the sun has also longitude, always calculating westbound. So that is 313 degrees. So you start here, it's 90, 180, 207. So it's about here. So that's where the sun is. So all the way here, that's the Greenwich hour angle, from the meridian all the way down there. So now the difference between us, the local, hour angle, that is, I write it here, from the boat to the sun. So the local hour angle goes from the boat to the sun. This is my local hour angle. And if you do this little sketch, you can easily see that it is always, when you are on western longitude, you take the Greenwich hour angle minus, and then you deduct my own longitude. That is the local hour angle. So if you don't want to do the sketch, you can then here look at footnote number 13. Footnote number 13 says, choose longitude in order to leave local hour angle as full degree, subtract for west longitude, that's where we are, and add for east. So we want to subtract. Subtract means that we take the local hour angle and deduct our own longitude. So now the question goes, which longitude do we choose? So when we subtract them, it becomes 0, 0 minutes. Well, it is very easy, because if you write 14.6 here and you deduct these two figures, it becomes 0, 0. So we have to write 14.6. That is our assumed position in minutes. But what degrees do we choose? Well, we need to be somewhere in vicinity where we are. So we are at 10 degrees 38. And 10 degrees 38 needs to be in vicinity of something which has 14.6. So let's test to say 10 degrees and 14.6 minutes. So if we say 10 degrees 14.6, how far is that from that position? Well, it's less than half a degree. So that is the closest. So 10 degrees and 14.6 minutes, that is the longitude of our assumed position. It's written in red, bum, bum, bum. It goes down here, 10 degrees and 14.6. Never mind the 0.6, because we can't draw it in the chart anyway. But if we want to be precise, we move the 14.6 down there. So what is the local hour angle then? Well, that is, if you deduct these two, this becomes blah, 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 0, 0, of course. And this is 3, 0, 3. So our local hour angle is 303 degrees. Why did we do all this? Because this local hour angle, you can see the shaded area here, has the same color as we need in that book. So we're done with step number 2. Now comes step number 3. Step number 3 is, I've made a little checklist here. Find a page in the site reduction table, which is called HO249. Well, here it is, 249. So our job is to find first the working latitude. Well, the working latitude, what is the working latitude? Well, it comes from here, doesn't it? So we think we are in 42. So we write that 42 here. So 42. Let us see, where is 42? Have I done something in here already? I don't know. Because 42 is about the latitude where we're going on. Yes. So this is latitude number 40 or 42. The next step is you look at the declination range. You look for 0 to 14 or 15 to 29. So 15 to 29, that's where we are with the declination, because the declination is 23, 21. So here it is. And then we need to make sure that we are on the same hemisphere or on the contrary hemisphere. No, we are on the same hemisphere. Because look here, it says north north. So the sun and us are both on the same hemisphere. So now it's very easy. So now we just look up the column of full degree of declination. So we look here, 23 degrees. We have 23:21, I know that, but the 21 minutes of the declination we take care of later. So first we look at the full degree of declination, and then we go there, row of local hour angle. So we have to go down to our local hour angle of 303. So where is 303? It's all the way down here. So that's a bit tricky when you're seasick and the boat's moving. So boom, 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 here. So that, another check, that's the middle one here. So these are the figures that I will copy. The HC is 39.21. 39.21. The D is 35. And it's positive because it doesn't have a minus. And the Z is 93. 93. So I've just copied these three figures. So we can close that again and continue here now and see what this means. So the HC, that is the degrees on the sextant I should measure 39.21 if I was on this position with the 23 degrees declination. Now the sun isn't 23 degrees, it is 23 degrees 21 minutes. And these 20 more minutes means that the sun is actually a bit closer to us, right? So it's not on 23 degrees, it's 23.21, so it's closer. So we need to consider that we should measure the sun a bit higher than the 39.21. How much higher? Well, that is the D factor who helps us how much we should take the weight that we should use to consider the 21 minutes. So that's what we do in this little sub-program in that box. Z is almost the azimuth. Let's start with the azimuth because that's the most logical thing. So we have the azimuth calculation box here. So if the local hour angle is bigger than 180 degrees, then it's morning. Well, it is bigger, so we are actually in this box. In the afternoon, we are here. And if we are in a northern latitude, then, which we are, then the Z that we were reading off there is the azimuth. So, great, cool. If not, we would have needed to do some calculations here, add or subtract 180 or 360 degrees, and for that case, for that sake, I have that little box here, so you easily can do the calculation which is requested. But in the morning, on the northern hemisphere, the 93 is just what it is our azimuth. So that we write down here because it's red. It makes sense, doesn't it? So the sun is at 93 degrees. It has an azimuth. The direction of the sun is 93 degrees. Of course it does, because it's in the morning. It's in the east. The sun goes up in the east and goes down in the west, even on the southern hemisphere. Okay, now we have this strange table number 5, which many people are struggling with. And I admit it's not the most logic thing, but you have to think of that this is actually only a way to calculate how much of the 21 minutes should you actually consider that HC should be increased. Well, you should not take the full 21 into consideration. You should only use 35/60th. So you can do it in your head or on your calculator, whatever. 35/60th of 21 degrees, 21 minutes. That's what we have to add to the HC. And for that sake, we have that table number 5. And if you've done it a couple of times, it comes as second nature. So here you have the D, how much weight you should use for the minutes. So if D is 0, you shouldn't consider anything. If C is 59, you should consider everything. So here the D is 35. So you take 35/60th off the 21 minutes. and the 21 minutes is here. So if you look there, 21 minutes, 60th, so that's 12 minutes. So 12 minutes we need to add to the 39.21. So it's not 39.21 we should have as HC, because that is only valid for 23 degrees of declination. Since the sun is at 23.21, we have to add these 12. That means 3, and that is 3. So we should measure 39.33. What did we measure? We measured 38 degrees 53. We should measure 39 degrees 33. So we measured something smaller. If we measure something smaller than we should, well, we are further away. That's red, we can go down there. How much further away? Well, you put the bigger figure here, that is 39 degrees 33, and ours, what we measured, 38.53. So you can see that the difference here is exactly 40 minutes, and that means 40 nautical miles, which I put down here at the intercept. And next time, when I do it, tomorrow, it's going to be much faster because I don't explain so much. I'm just going to run down the calculations. So that's good. So this goes into the chart, but we want to wait until we have the noon sight. And the noon sight, I have another template because we're trying to do the noon sight. The issue is that it's a bit cloudy, so it's not so easy, but maybe the front, the occluded front is going to move away. So let's prepare the noon sight and just see when will noon be. So here's the noon sight. So it will still be the 16th of June. Our estimated lat and long. Well, that's the thing. Now we know where we were in the before, and then we have to calculate where we're gonna be approximately, and which log we have. So that is what we can do. We can approximately find out where the meridian passage is, because we know that now we are at some 10 degrees. We will be around 11 degrees approximately. So that's why we want to know if we are at 11 degrees longitude, when do we have noon? For that sake, we need to check when is it noon at Greenwich, at the meridian passage in London. Well, 12 o'clock, isn't it? More or less. So if you want to be very precise, we can actually look up on the daily pages here in the almanac when we have the meridian passage. So you can see here, so that's 16th of June, that's here. So the meridian passage is 12:01. Well, never mind that minute. But anyway, it is very close to noon. So that means that we can write 12:01 here. And now the question is, when will we have noon? Well, if we were in London, it would be at 12:01. But now we are 11 degrees further west. So it takes some time for the sun to move here. It moves 15 degrees per hour, so it should be a bit less than an hour. If you want to be really precise, less than an hour, what you do is that you look at the arc to time table, which I have. Where's the arc to time? I think that's table number 3, is it? Here. Table number 3. And I have a footnote where you can find it. Arc to time. So this is the sun's movement. So in the 15 degrees, it takes 1 hour to move. So we say we are about 11 minutes. So, we are 11 degrees further west. So that takes 44 minutes. It comes without saying, actually, doesn't it? So 11 degrees is about 3/4 of an hour of the 15. So 44 minutes. So right here, 44 minutes later. So we will have noon at our position at 12:45. What time is it now? Two more hours. That's good. That's perfect. So we can have a break. Why do we calculate this? We do it for two reasons. First of all, when should we go up and shoot the sun? So the good thing is that you go up maybe 20 minutes before and check it rising, and then it stands still for about 20 minutes and then it goes down again. And the second thing is that we need to check what is the declination of the sun at that time. So that we can look up later. But this is important that we know that in about 2.5 hours we can do the noon sight. So let's see you then.
So hi, it's about noon now, ship's noon. It's 12:30, so it's 15 minutes to go according to our calculations. We don't really know where we exactly are, but about 15 minutes before you should get up with your sextant. And the good thing is you don't need a watch this time, because all you have to do is to catch the sun when it's the highest. And the sun is in the clouds, but you still can shoot the sun nicely through the clouds. So don't be mistaken just because you have high clouds. It's still rather sharp if you have a sextant with good optics. There, that's what I have now. It's 70 degrees and 34 minutes. Well, okay, went up a bit more. So it's 70 degrees and 37 now. So check it. Well, that's it. Whoa, 70-39. It does still go up. So all we have to do is now wait and see when it is the highest, and that's what we're going to note, and that's ship's noon. So that's what they did in the olden days. You know, they sailed down due south, and then they turned west. Sun's in the clouds now. I have to take away some shades. Very nice and short. 44. 70 degrees and 44 minutes. 70 degrees 45. Still going up. .46. I don't need the watch. That's a good thing. Okay, 48. Well, 50 now. Surprisingly accurate. Oh, 53. Yeah, 53. It's 53 all the time. 53. 53. Well, I get this one as 52. Meaning that we've been on the top maybe. And it's 12:45. So we have been out doing the noon sight. The engine is running. We have only some 11 knots of wind, headwinds on the Atlantic, but no waves. So it's quite comfortable. So I have enough time to do a little celestial navigation. So what Nick had done is to do the estimated position on this chart, but it's very small scaled. So it's quite good to start with your own chart that you make by using a plotting sheet. And I have developed or improved the most available plotting sheet like this, so it's easier for you to build your own chart, so to speak. So where you start is that you choose the latitude that you want to be on. And if you remember, on my template, on the very bottom, I have the red box, and on that red box, that is the data, the only data that I will be using to draw my celestial navigation on that plotting sheet. So I start with my latitude that stands on the top, and my working latitude is 42 degrees north. So I write this here, and then you can jump up one step, and there it says plus or minus here. And plus and minus has some color coding. So plus is on the northern latitude. That means that if you go north, because this plotting sheet you can also use on the southern latitudes, if you go north up on the chart, it has 1 degree more. So this is 43 north, and the equivalent is 41 north here. So these are the latitudes. The longitudes here, there I can also choose my working longitude,
and it should be close to the one that it says in the red box, 10 degrees in 14 minutes. So let's call this then 10 degrees here. Now the question is, does it increase or does it decrease depending on if you go west or east? So we are on western longitudes, and that means that if we go left, they increase. So that's why you also have the color coding here. So this means that this is 11 degrees west and this is 9 degrees west. Had we been on eastern longitudes, then it had been the opposite. It all says in the color coding down on the right bottom corner. So this is 10. So where is now 9? There's no line for 9. And that is because we have the Mercator projection. So the further up north we get, or south, close to the pole, the smaller become the latitudes. On the North Pole, it's very fast to go around the whole pole, around the whole world, just to walk a couple of meters around the North Pole. And along the equator, it's the longest because that is the only great circle you have as a latitude. So here's a little hint. So we have 42 degrees north, so we can go here and go up to 42 degrees. So 10, 20, 30, 42. It's all only to draw our own chart. So that's 42. And then we have a little mark here, 42. And the same equivalent here, 42 and 42. So this is now where I have to connect them with a ruler. So I connect these vertical lines here by means of a ruler there and here. So these are now my longitudes. You could use a divider and measure also here. There's an arrow down there, 42 degrees, that is this and this. So you can make a circle around there. This is the only the place where you should measure your longitude. So you can take the divider and measure from there to there, and that is 1 degree. So if you measure it here, it should be exactly the same thing as using these points that I have been having as help points up there, down there, up there, down there. So this is my chart. So it's not more difficult than this. So now I should draw my assumed position. So that is along the 42 north, it says here, and it has 10, 14. So this is 10, and now 14 minutes more than 10 degrees. So that means 14 into the western direction. So I take my divider, look where is 14 minutes. So not making holes in my remarkable. So this is my assumed position for the morning. Assumed position number 1. 42 degrees north and 10 degrees and 14.6 west. From here, that is where I would like to have the azimuth. And the azimuth is going 93 degrees. So I could take this plotter here, if I wanted, and put it on 93 degrees, the Portland plotter, and then turn it through that point, have it in parallel, and then I have my azimuth showing towards the sun. So that makes sense because that is the sun in the morning. So that's the direction of the sun. So now I want an intercept of 40 nautical miles, and that is away, so I place it away from my assumed position. So the 40 miles are only measured along a great circle, meaning along this longitude. So I have to prolong that line a little bit, and then I measure 40 nautical miles away from my assumed position. So I am actually somewhere here. So this is where my position line goes through. So 90 degrees to that is where my position line is. So that's my first position line. I'll make 2 lines there in those directions. So that's approximately where we are. Now from here we are now have been sailing on. So what I need to do is I need to move this line as long as I have been sailing. So the log was 142 degrees when I was doing the morning shot, and in the evening it was 165, because I noted that down, not in the evening, in the noon sight, 165. So that means that I've sailed 23 miles. So I've sailed 23 miles. In which direction? Well, the direction of our course. And we have sailed 260 degrees. So I put this on 260. There we go. And so I've sailed that direction for, what did I say? 23 miles. So I measured 23 miles in the middle on the longitude and say, this is the distance I have sailed. So that means that that line needs to be moved in parallel. So this is my moved position line. So along this position line I am in at noon sight. So all I need to do now is to know what my latitude is. When I know my latitude, I know my position. So let's go and back to my template for the noon sight, which we already have started with a little bit. So that is very easy. So what we do now is just to check step number 2 here. What is the declination of the sun at 12:45? And for that sake, I need to get my calendar, my nautical almanac, and it's still the 16th, but now it's 12:45, and you can see here the 16th. So at 12 the declination was 23:20.9, and at 13 it's 23:21.0. so it's closer to 13. It's only 0.1 minutes apart, so let's call that 23 degrees 21. 23 degrees 21 minutes. So that's the declination of the sun. And then we have the sextant that we measured. The sextant angle, the angle on the sextant, the altitude, that was, if I recall correctly, 70 degrees and was it 53, right? 53 minutes. We don't have an index error, so it's still 70 degrees, 53 minutes. So if we go now the RYA way, we have a dip. It's always the same. It's on the yellow page. I was setting on the coach roof. It was 2.5 meters high up. So it's 2.8 minutes. So it's minus 2.8 minutes. So then we get the apparent altitude. So that is as much as, let me see, that's 0, 70 degrees and 50.2. Then we have the sun correction in the yellow page. Then we have April to September. We measured some 70 degrees, so that is between these two. So it's plus 15.6 for the lower limb. 15.6. So it's 15.6, always positive. So that is 8. That is 5. 5 plus 1 is 6. That means a whole degree. So it's 71 degrees and 5.8. Of course, we could do it the quick way. So if it's between 55 and 80, it was closer to 80. So we just add 13 minutes to this. Go down this way. Just add 13 minutes. So if we add 13 minutes, comes 6 in the end, and that's 0 there, and 71. So it becomes 71 degrees and 06 minutes. And the long way, it was 71 degrees 05.8. So it's hardly any difference. So that's what I'm saying. You have to do some calculations in your head though. But that fast one is really good. Okay, so now comes the really easy step number 4, there where you have this thought here. This illustration is for summer, where we normally sail. But if you have any other times of the year that you're sailing, you can use here these hints that I have there, or draw your own little chartlet. So we are on the northern latitude The sun is on the northern latitude, the declination is on the northern latitude, and as you remember, the zenith distance is that the distance between us and the picture point of the sun, which is there, which is 90 degrees minus HO. You only have to add the declination, and then you have your latitude, which is from you to the equator latitude. So what you do is you calculate first the zenith distance, 90 degrees minus HO. Here it says 90 degrees, but I changed it to 89 degrees and 60 minutes, which is 90 degrees, but it's easier to calculate. And the true altitude comes from here, 7106. So we take the difference between that. So that is 4 and 5, and that is 8, and that is 1. So it's 18 degrees and 54. Is that correct? Is it? I think it is.
Yep.
So then we add the declination, and the declination we come from up here. You can see the arrow there, 23, 21. We add those two, and that's 5 and 5, 6, 7. That would be 70 minutes. So that's 1 there, 1 plus there. So it's 8, 9, 12, 2, 3, 4. 40 degrees, 42 degrees and 50 minutes. That is our latitude. So that's good. So all we do is we add the latitude there back to our plotting sheet, which is here. 42 is here, and 15 is there. So we put the ruler there. Here we have a fix. That's our fix. That is our fix. So what's our fix? So the fix is 42 degrees and 15 minutes north, obviously. And now this fix is a bit to the right of 11 degrees. So we go here, that distance. How much more? We measure it here. 1, 2, 3, so that's 30, 32. So it's 11 degrees 32 west. So that's our fix. Isn't that cool? And we're not allowed to compare that with the GPS according to the RYA. But that is the fix for Nick when you do it tomorrow.
Yeah.
So over to you for tomorrow.